All right, we're going to kick off today's session. Welcome again to our live roundtable. In this session, we will explore RunSafe's efforts to help developers and product owners embrace secure by design practices, as well as lessons learned in achieving memory safety protection and its value across industries. Today, we have the pleasure of hosting RunSafe's Doug Britton, Executive Vice President and Chief Strategy Officer, and Shane Fry, Chief Technology Officer. They will share their insights on this critical topic, addressing the persistent challenge of memory safety vulnerabilities in the software industry, which have led to numerous security breaches and compromised systems. Before we dive into the presentation, I just want to go over a few housekeeping items. We will keep everyone muted until the end of the session. Please feel free to add your questions at any time in the chat, and we will address them during the Q&A portion at the end. At the conclusion of the webinar, we will send you a link for your fun virtual swag bag. To get things kicked off, let's introduce our speakers. Doug, would you like to get us started?
Thanks, Stacey. So I'm one of RunSafe's co-founders. I focus on our intellectual property strategy, our technology strategy, and our partnerships. I got started in cybersecurity about 20 years ago while I was at Lockheed Martin, and I was in the cybersecurity aspect that focuses on facilitating access to intelligence objectives. Prior to that, I was in Army intelligence. I was a humaniter and Russian linguist.
And Shane, would you mind providing a brief overview of your experience?
Thanks, Stacey. I'm the CTO here at RunSafe. My background is in vulnerability research, exploit development, software developer by trade, but have been on kind of the offensive and defensive cyber side of things for over a decade now, and have been at RunSafe here for over 6 years, leading our development team as we try and tackle some of these memory safety problems and provide solutions to developers, software companies, both big and small, to help them prevent these memory safety vulnerabilities from being catastrophic.
Great. Thank you both for doing a quick intro. And so we're going to jump into the agenda here for today. And we want to start off with Doug. Doug, could you please provide an overview of the challenges developers and product owners face in achieving memory safety and the potential consequences of memory safety vulnerabilities from your perspective?
The classic memory safety issues are amongst the oldest and most insidious class of issues in software. We've known about them for decades, but we have yet to operationally eradicate them. So testing hasn't found everything, and neither have compiler tools. So you never know that you get them all. There's always this risk and frankly, the statistical likelihood that you've missed some. This class of bugs are commonly used by criminal organizations and nation states in hacking efforts. The White House and the Department of Homeland Security have put out separate research and guidance that shows that 2/3 of the vulnerabilities in compiled code relate to memory safety issues, and that those are commonly weaponized by criminal elements and nation states. So getting it wrong means an attacker has an almost undetectable ability to get into your device or software and get it to do the attacker's bidding.
Thank you so much for that, Doug. And to follow up with that, secure by design has often been referred to as the ideal approach in software development. But obviously, we know that the challenges that some of our clients are facing. What are some of the key barriers that we've seen that one faces when trying to adopt secure by design practices, and how can these be overcome?
Secure by design and secure by default are fantastic advancements in secure systems paradigms. They're undoubtedly going to make things much more secure over time. The challenge is that secure by design has this requisite transition to memory safe languages, which isn't feasible economically or in any other fashion feasible in a short timeline. Most vendors we've spoken to have said it's going to take them at least 8 years to get an appreciable portion of their code running in memory safe languages. It's unnerving to think that we're going to cede 8 years of risk to our adversaries waiting for perfect. Defenders have an alternative, which would be allow the mitigation of the exploitation risk of entire classes of vulns without rewriting the software. These economical approaches can allow for 40 to 70% of the vulns to be mitigated, gigabytes and gigabytes of code, without changing one line of software. So that really sort of, splits the baby in being able to mitigate the risk without having to invest billions and billions of dollars in rewriting code.
Thank you for that. And I want to jump it over to Shane, unless Shane, you have any responses to anything that we've discussed with Doug so far.
What I would add there is, I think there's this gap that Doug's talking about between what we have today and the ideal paradise of secure by design, and really looking to how do we bridge the gap today. It's great that we can plan for 5, 10, 15 years down the road, but we've got to do something today, because those bugs that exist today are going to be exploited tomorrow. Attackers aren't going to wait 15 years for us to get secure by design devices into consumers' hands. So, that's very important that we act today. And, even when we think about secure by design, everyone really kind of focuses on Rust and Go, writing in secure languages, memory safe languages. But the ugly truth is that if you look at Rust crates and Go libraries, it's possible to write unsafe code and have unsafe code get brought into your software without you even knowing. So, even if we shoot for 10 to 15 years from now, everything's written in Go or Rust or some other memory safe language, there's no guarantee that you're actually going to be memory safe in using that language.
Great. That actually leads me right into our next question. So I appreciate that feedback. So before we kind of jump into how RunSafe can help with memory safety, first I would like to just kind of provide a high level so the audience knows what memory safety means and why it's important. I know we've addressed this so far from a high level, but just want to kind of break it down specifically to memory safe practices and really what it is from a general description perspective.
Yeah. So when we talk about memory safety issues, we generally are talking about memory that's being read more than it's supposed to be or written more than it was supposed to be. So a program might allocate 10 bytes of space to store some string. If you can write 20 bytes or 30 bytes or 40 bytes, you can overflow a buffer, you can overflow some data on the heap, and attackers can leverage that to take control over the system, or in the case of maybe a memory overread situation, they might be able to read sensitive data out. So if you look at like the Heartbleed bug from forever ago, people's private encryption keys were getting leaked out through a buffer overread situation. And so, as we think about them, technically that's kind of what's happening, right? Memory is being either read or written to when it's not supposed to be, or you've got cases where memory is being executed when it's not supposed to be, or from the wrong place. But from kind of one level up from that, memory safety bugs are 40 to 70% of all bugs that are fixed in software today. That number comes from both Microsoft and Google, but it aligns pretty closely in the OT ICS space as well, where the number's a little higher, about 72%. And these bugs are in software, as Doug mentioned earlier, they're very hard to find. Static code scanning tools from a study from North Carolina State only found 2.5% of vulnerabilities that were identified in open source software over a 10-year period. And so, that's pretty alarming, right? And so we can't find them. They live a long time. They're in code bases for anywhere from 2 to 5 years on average, depending on which study you look at. And, some of the most devastating security bugs, as far as like the CVSS scoring, are going to be those memory safety bugs, right? They're the ones that allow remote control of a device. And so that's really why RunSafe is focused in that area. We want to be really focused on high impact security issues that we can mitigate and mitigate well for our customers.
And Shane, could you please explain to us how RunSafe helps achieve memory safety protection and why this is so valuable to the industry?
Yeah, so as I mentioned earlier, finding all these bugs in your software, it's hard. Microsoft and Google spend so much money and they can't get it right. So how do we expect everybody else to get it right with much smaller budgets? So at RunSafe, instead of trying to play whack-a-mole and find every vulnerability and find all the unknowns, we're taking a different approach. We said, hey, let's use Doug and I's expertise in how attackers take control of systems, how they weaponize these vulnerabilities, and use that to take those tools away from the attacker. So as attackers find buffer overflows and heap use after freeze, what they then do is use what's called return-oriented programming, ROP, or jump-oriented programming, to have code that's already loaded in memory execute. And so what we do is when a protected program is running or is a protected library is launched, we randomize where all that code is in memory. So we change the order of all the functions in memory. So it's kind of like address space layout randomization, but it's a whole nother level of that. And so what that does is that when the attacker finds that buffer overflow, they can send all the bytes that they want to take control of the system, but they don't know where to point the processor to go execute the code that they want to execute because that code's been randomized. So that allows us to have a really slick integration at build time and protection from both known and unknown vulnerabilities at runtime long after the device has already been fielded. Maybe it even never gets patches, right? We see that a lot in the OT and ICS space. So you get kind of that forward protection for software and for devices that have our protections in play.
What we've heard from our customers is that RunSafe is really the perfect balance of easy to use while mitigating entire class of vulnerabilities without impacting device performance and reliability. And these are the key things that, manufacturers of weapon systems and critical infrastructure really need to know, have confidence in their systems. People are able to get started in minutes. And the other thing is it allows developers and customers to put their focus on other aspects of secure by design, taking a responsible approach to adding, memory safe language-based code as the support expands, but without having to do it on an emergency basis. And our customers have found that it allows them to keep focus on product features and product advancement without having to, take too much focus off while they're still able to put forward progress on the secure by design advancements.
We're all aware of the importance of secure by design principles. We're here talking about it today. Shane, could you share with us what RunSafe is doing to help adopt these practices and some of the lessons that we've learned along the way?
Yeah, so the big thing when people talk about secure by design, by and large, is moving to memory safe languages. And to that extent, RunSafe took the portion of our code that runs on customer devices in customer software and we ported that from C++ to Rust. And that was not a very easy process. We have a relatively small code base, but it still took us, over 6 months to get that process moved over, all that code moved over. And, we did a lot of extensive testing on that to make sure we didn't introduce any new bugs. And actually, as a result, we found a bug in our C++ implementation because of Rust bounds checking and safety things there. So, we went back and backported that to our C++ branch. So we had that in case we ever need our C++ branch. So that's kind of the big thing that people think about with secure by design. But the other thing with secure by design is generating software bill of materials, and RunSafe has a great solution for that, for building SBOMs for everything from interpreted languages, JavaScript, Python, to compiled languages, C, C++. We have a really novel solution for generating those software bill of materials at software build time, and we're expanding from there. So secure by design is designing something secure, but also making sure that your supply chain is secure, the vulnerabilities that you have in that software bill of materials you generate are mitigated. And so, the RunSafe code product is able to provide those mitigations for software that you're compiling. Our repo offering helps you have pre-hardened open source software that you can deploy to mitigate vulnerabilities in the open source in your supply chain. And we've also got software bill of materials generation that all kind of fit into that secure by design ecosystem. And coming soon, we're going to be releasing software bill of materials for our own product offerings. So alongside of our releases, you'll be able to download a software bill of materials and understand exactly what's in our supply chain as well. We think it's really important to not have that hidden or held back. We see a lot of protection of software bill of materials by companies in the commercial space, and it really doesn't make sense, right? If a vendor of ours can say, hey, you've got this vulnerability, are you aware of it? Hopefully our internal processes catch it first, but we'd much rather have someone report that to us because they saw it, because they ingested it, and have that as part of their secure supply chain initiatives as well. So we've got a lot of stuff that we're doing in that space, and there's definitely more to come. I don't want to spill all the beans on this webinar, but we got a lot more coming in that space too.
Yes, we do. And it's super exciting for sure. So, one thing that RunSafe focuses on is helping to secure embedded software that's deployed across critical infrastructure. Doug, can you kind of walk us through RunSafe's approach to software memory protection and compare it to the adoption of memory safe languages?
Partners and customers in critical infrastructure realize that without having to, again, rewrite software on legacy devices that are in their development pipeline, they're able to get rid of an entire class of issues, simply by recompiling and deploying. What they're finding is that allows them to forego, so many random patch updates that are required when there's a new vulnerability that's discovered. So, they're able to save millions on the labor of recreating what already exists and, years of delay per application. So the other thing is they can have these mitigations in place, immediately once they recompile instead of having to wait, months or years while the software is being rewritten. And that, that time is, by being able to have it in place, that decreases the probability that their system is why a county's water system or a county's electrical system ends up in the news as a part of a ransomware attack. And that's just been hugely impactful.
Yep. And what I would add there too, Doug, is as we look at OT and ICS, Rust and Going have great support on Windows, on Linux, on Mac for Intel and ARM targets, right? The standard desktop operating systems that people are using today. But once you start getting off the beaten path a little bit, support for those memory safe languages is pretty rough. There's definitely some work to make that better, but we've seen in our efforts to build support for things like Yocto and Buildroot and things like that getting Rust stuff to build for those ecosystems can be challenging, if not downright impossible, right? We'd love to support older versions of VxWorks with Rust, but the support's just not there. The Rust community is not going to build it. And Wind River is building all their support for Rust in VxWorks 7. So what are, people on VxWorks 6 going to do? Well, now they're looking to get memory safe, they've got to move to an entirely new major version of an operating system on top of that. So, all great points and, things that are challenging for the OT and ICS space, for sure.
Great, thank you. And I know one of the things that can prohibit someone from implementing memory safe languages in existing code bases that have been around for years and years and years is, among other things, cost, which, we've already spoke to, but one thing would be just the resources that someone perceives it might take to implement a memory safe, practice in their existing code base. So can we just quickly review, how easy is it to actually get started with, RunSafe, and what type of resources are we looking at as far as someone needing to have internally to implement this?
I'll say, and I'll get out of the way quickly. I mean, you make a really good point, Stacy. It's easy to forget that to be able to implement Rust, it's not as simple as downloading a module like you're in the Matrix and you just now know Rust. I mean, it's a language that needs to be learned and mastered, and it's taken us decades to write the body of C and C++ that is now the core of the internet and the core of IoT and embedded devices. It will take, an equivalent amount of time with an equivalent number of developers to transition that body of code to something else. And where those developers aren't coming out of nowhere. I mean, some colleges are starting to teach Rust and have Rust as the basis of their programs in CNC in computer science, but that's still lagging. So, for that transition to happen, we need a body of developers that, as of yet, just simply doesn't exist. And so Shane, with that labor aspect in mind, I mean, please go ahead and explain, the mechanics of what it takes for someone to get started with RunSafe.
So, one of the things is we want our solution to be easy to integrate. And so most of our customers get it integrated in half an hour to an hour. They spend more time testing and validating than they do integrating. For pretty much every environment, it's as simple as installing our packages. We've got a Yum, Debian, and Red Hat repository where you can just do an apt install or a Yum DNF install and get our build packages, and then it's a one-line change to your build environment. So if you're using make, you'll make that LFR helper make. If you're doing CMake, same thing. If you've got some build script from 40 years ago, that also just works. There's some edge cases here and there, but for most cases, our customers are done in half an hour, and then you're done. We have build tooling to make that really easy, and then we've also got tooling on the debugging side. So our customers that are using GDB to debug their applications, they don't have to worry about, well, is this randomization in place? Is it not? Is it working? Is it not? We have a plugin for GDB that just allows you to debug as you normally would. So we really try and make it really simple for the programmers, and you can do the integration on a kind of one-off basis per project, or we've got some customers that are doing DevOps pipelines and they've got kind of a build image that all their software builds in. We've got really easy ways to integrate with that so that any software that builds in that template gets the protections baked in. And then for things like Android or Yocto or Buildroot or Timesys Factory, we've got really easy drop-in solutions that are native to those build systems that allow you to just, in the case of Yocto, just add a layer to your existing Yocto image and off you go. Do a build as normal. So, we really do try and make it super simple. And our website has, documentation with the step-by-step, and we get a lot of great feedback on how easy it is to integrate.
Great. And I know you mentioned, whether your code base is 40 years old or a year old, are there any limitations as far as the age of your code base in this relation?
Not really. We've got some customers that they literally have code that was written in the 80s that we're protecting today. And we've seen all kinds of strange build systems. So our primary limitations are just the operating system that your system's running in and the processor architecture. So today we have support for Intel and ARM, 32-bit, 64-bit, as well as PowerPC. And then on the operating system side, we support Linux and all of its variants, Android, et cetera, and VxWorks, and we're building support for Linksys 178 so that we can be in safety of flight systems. So that's really exciting. And we're planning to do support for QNX as well. So a lot of different operating systems, a lot of processor architectures. If you've got something that's outside of those parameters, please reach out. We're always willing to entertain building new processor architecture support as well as new operating system support for the right opportunity.
Thank you, everyone. I hope you enjoyed the session today. Thank you, Doug and Shane, for your contributions. We hope that their expertise has shed some light on the importance of memory safety and secure by design practices. Now we would like to open the floor to our audience for a live Q&A. We have some time for several questions, so please don't hesitate to share your thoughts or inquiries in the chat. Again, just to participate, you can simply use the chat function to submit your questions, and we'll do our best to answer them in the time remaining. Just as a point of reference, if you are interested in the swag bag, if you could send us a confirmation in the chat, that would be great. But we're going to start off with a couple of questions here. So Shane and Doug, how do you see CISA's Secure by Design overlapping with the EU's Cyber Resilience Act?
So I think there's a lot of commonality there, driving at a very similar set of challenges. Both are, driving at transparency. Both are, encouraging or in many cases compelling people to be clear about, what are in the contents of their software and devices they deliver. So that allows, buyers to understand the risk of what they're adding into their environment. So that's something that is, I think, common to both.
Great. And Shane, can you explain more on what types of memory corruption vulnerabilities such as buffer overflows, does RunSafe solution mitigate most effectively?
Yeah, that's a great question. So, we at RunSafe are really focused on memory corruption, memory safety vulnerability. So, there's about 86 of them that CWEs, common weakness enumerations, that we can provide mitigations. As you mentioned, buffer overflows, heap overflows, some type confusion, bugs, integer overflows, things like that. Really, any weakness or vulnerability where an attacker is going to be able to take control of the processor and get it to execute code in another place. And we're really focused in that area. So, we're not looking at web application security or, hard-coded login credentials or, bad crypto implementations. But we're really focused in kind of the 86 or so CWEs that are related to memory safety.
Great, thank you for that. And another one here, how does RunSafe address the challenge of protecting existing and legacy systems that may be difficult to update?
Yeah, we integrate our software at build time. So obviously, for devices that are hard to update, you still have to do one update to get RunSafe there. But one of the things that's really great is we're leveraging existing capabilities in build tooling that has been around for decades. And so, we can work in really old, antiquated environments. As I mentioned earlier, we've got some customers that are, protecting code that was written in the 80s. So, 40 years ago or so. And so we work really well in those environments. And one of the really cool things is because we're not a heuristic or some, AI tool or antivirus where you've got to have, updates all the time, you can ship devices today. And if those devices with RunSafe, if those devices never get a patch, they're still going to be protected against those vulnerabilities. And so it's a great offering for both new development as well as legacy devices and software that can provide you kind of future proofing against vulnerabilities that you don't know about today.
Great, thank you. And Doug or Shane, whoever this would be most useful in response to, will ASLR, or address space layer randomization, as we know it, options natively offered by modern OS compilers help alleviate the memory safety issues?
Yeah. So ASLR has been a part of operating systems beginning in roughly the 2006 timeframe. And unfortunately, we have seen that, memory safety exploitation has not remotely abated. It hasn't slowed much at all. Not long after ASLR was introduced, ways were demonstrated to reliably and scalably counter it. It doesn't. The chief challenge with ASLR is it doesn't provide enough granularity. It's not nearly specific enough, or there's still too much predictability in where code snippets lay in memory for an attacker to be able to, they're still able to reliably stitch together an attack.
Great, thank you. And we have one last question. Can you share any use cases or case studies where RunSafe's technology prevented a potential security breach?
Yeah, so we've done some work with an industrial control systems manufacturer that we won't name, and we went out and looked at, based on a software bill of materials for one of their devices, found some vulnerabilities, and went through and actually did kind of the end-to-end exploit against it. So this happened to be a remote execution vulnerability in the point-to-point protocol daemon that was unauthenticated. So even though that daemon has authentication and you can set that up, you can actually exploit this vulnerability without any authentication needed. And so, we were able to show them how their devices were vulnerable by actually exploiting the device and, creating an effect on the targeted device. And then we worked with them to integrate our protections into that device, and then reran the exact same exploit, modified a little bit for the new program that was compiled, and showed that it was no longer able to be exploited. So, we don't have an example at the moment of someone in the field with, a real threat actor attacking a target system, but this is a vulnerability that would be very much the viable in the real world. It was a real world vulnerability on internet connected devices, so very relevant.
And how does we have a good question here. I thought it was the last one, but we have a good one. How does our solution compare to Sternum?
I'll take a couple of swings at that, Shane. I know you'll have a couple of other thoughts. So, Sternum, what our customers have found, and I'll be, if people should follow up with more specificity, and we could go into more detail in a one-on-one conversation. But what our customers have found, kind of unparalleled in the market, is that the ease of integration, the combination of ease of integration and strength of security guarantees, is extremely unique. And the other thing is that our approach to a lot of our customers in the aerospace and defense and automotive space, they've been excited about the fact that we're starting our safety certification process so that they will be able to add our code to safety certified systems, be it DO 178 for aviation systems or ISO 26262 for automotive systems, without impairing their current safety certifications. So those are a couple of things that have been our customers have found compelling and exciting. Did I miss anything, Shane?
No, that's pretty good.
Great, thank you. I appreciate it. Well, that concludes our webinar for today, and we will be following up with everyone that attended to get you your swag bag. And if you have any other questions, please feel free to reach out, and you can find us at runsafesecurity.com. Have a great day.